Okay, so we will continue the class lecture on section 7.4. After proof that the first two propositions, now we will prove a major proposition in this section called Schwarz inequality. Okay, so we let x and y be random variables with finite second moment. E of x square and expectation of y square. Right. Then the product of x and y has a finite expectation, and the square of its expectation is less than or equal to the product of the two second moment. Okay. Okay. Right. So this is an equality, and the equality holds if and only if either y equal to alpha x or x is equal to beta y. Okay, with probability 1 for some constants alpha and beta in R. Okay. All right, so at the beginning of the proof, we will consider two special cases. So if the second moment of x is 0, okay, all right, so if it's 0, then we know that x is equal to 0 with probability 1 by proposition 7.4.b, right? We just proved before. Okay. So x equal to 0 is probability 1. Now, if we multiply both sides by y, then so that's x times y is equal to 0 with probability 1. Okay, so that the expectation of x times y is 0, okay, which is 0, and of course it is equal to so that it is equal to expectation of s squared, because this is 0, right? So maybe I will say as 0 times expectation of y squared, which is equal to expectation of s squared multiplied with expectation y square. Okay, so in this case, we prove this inequality here, and we know that x is equal to 0 times y, right? With probability y. Okay, so x, because x is 0, and just like x 0 times y, it's probability 1 with beta equal to 0. Okay, in the case here. So that this is special case we have. And similarly, if the second moment of y is 0, then of course y is equal to 0 with probability 1 again by proposition 7.4.b. Okay. All right. So that's x times y is 0 with probability 1. Okay. So when we multiply x on both sides. And 0 is equal to expectation of xy. Okay, and this is equal to square. So this is expectation of x squared times 0. But as we know, 0 is equal to the second moment of y. Okay, so now we have equality here, and we know that y is equal to 0 times x with probability y. Okay, and with alpha equal to 0 here. Okay, so if we have two special cases that and we have this inequality, and actually the inequality become to equality, all right? And in this case, we know that x is equal to beta times y. Beta is 0, and in that case, y is equal to 0 times x. Okay, so they also in these two special cases that they follow the conclusion of this proposition. Okay, so now we will go to C. So we assume now we assume that that the second moment of x is positive, and the second moment of y is also positive. Okay. All right, and so we want to show that that the product of x and y has a finite expectation. Okay, so and then we have this inequality, and then we will show that equality holds if and only if this condition is satisfied. Okay, so now to show this product has finite expectation. Now, so we let x head equal to x divided by the square root of this second moment, and because the second moment is positive, so the denominator is greater than 0, so this is well defined. And the y head is defined to be y divided by the square root of the second moment of y. Okay? Now, we look at the plus minus, all right? And we take the a square, right? So this square should be greater than or equal to 0 here. Okay. And so if we do the multiplication, we have the square plus the square will be greater than or equal to plus minus 2 to the product here. Okay, so we have this inequality here. Okay, right? So we have this inequality. Now that so since so we look at the expectation of let's say square, and this is equal to expectation of x square divided by expectation of x square, which is equal to 1. Also, expectation of y head square is the expectation of y square, expectation of y square, which is 1. Okay, so you can see the expectation of each term is 1, so they are finite. Okay, so so we have the expectation of this is sum. Is the expectation of the sum of the expectations. Okay, so this is from what? The linearity of expectation. Okay, so this is it. This is from proposition 7.2.a part 2, right? Part 2 there. Okay, or you can use part 1 that they. Okay, because they are non-negative. All right, so 1 or 2 are fine. Okay, so I just say, okay, 7.2.a here. All right, and this is, we know it's true, so this is finite. Now, this is has finite expectation. Okay, all right, has finite expectation. So that so now by proposition 7.2.b part 2, okay, we know this one. Okay. Oh, by the way, oh, okay. So this saying that this implies x square plus y head square going equal to 2 times the absolute value here. Okay. Right, and the equality is from proposition 7.2.a here. Okay. Okay. Now, so this one imply, all right. So this implies that expectation of x a plus this one is greater than or equal to expectation of x a y a. Absolute value here. Okay. This is by proposition 7.2.b dash 1. Okay. The reason why it is greater than equal to absolute value because that this is greater than either minus or plus. Okay, so you can whenever this product has positive value, you use plus. When this product has negative value, you use minus. So the lower bound is always can be replaced by the absolute value sign here. Okay, and so by this proposition, and because the both sides are non-negative random variables, so we have this one. We have that. Okay, so we have that, and from here we know this is equal to 2, right? This is 2 here. So that this implies that 2 greater than equal to 2 expectation of x hay, y hay here. Okay, and what is this? Well, when you plug into there, you will see this is 2 and divided by square root of expectation of x squared, expectation of y squared. Here we have that. And this is the expectation of xy. Oh, sorry. No, okay, not yet. Anyway, so that an application and implication is that the expectation of x hay, y hay is finite. So this means that expectation of x hay and y hay is finite. Okay, so that it is finite. I have to say, so it exists and it's finite. Okay. All right. So here we prove that the product of x and y has a finite expectation. Okay. All right. So from this computation, we know the finite expectation. Why do we have that? Oh, okay. So we don't need this. Okay. So we have, so that now we show that this product has finite expectation. Okay. Now to show the inequality. Okay, so now we consider that. So now okay. Now, since x minus y bar square is greater than or equal to 0, right? So this time we just use the difference. Okay. So this means that x hay square plus y hay square is greater than or equal to 2 times x bar x hay y hay. Okay. Maybe okay, sorry. We have the expectation of, okay, greater than or equal to 0. Okay. So it's because that yep. Because this is non-negative random variable is greater than it. So again, this is expectation of 0 is 0, right? So you can use by proposition 7.2. Oh, 0.4.8. Yeah, greater than. Yes, I'm sorry. It's incorrect. It's 7.8 dash 1. I'm sorry. Because 7.2.b is about the independence. Right. Okay. So so we apply 7.4.8 dash 1. Okay. Yeah. Okay. And here again dash 1. Okay. Okay. Now, and we look at see here, greater than 0, and equality holds. Okay, so the equality holds. Equality holds, right? If and only if only x hat minus x y hat, all right, x equal to 0 with probability 1. Okay, by proposition 7.4.b. Okay. Okay. So equality hold means that the second moment of this difference equal to 0. Okay, and it is equal to 0 if only if the difference is 0 with probability 1 by these propositions. Okay, right. Right now, but we look at here. Okay, it's equal to, so we do that. This is square minus 2, okay, plus y hat square. Okay, so we have linear combination of 3 random variables. The first one is the square of x hat. The second one is the product of x hat and y hat. And third one is the square of y hat. And the coefficient 1, minus 2, and 1. Okay, so this is a linear combination of 3 random variables. But we have shown that this random variable has finite expectation. Actually, is equal to 1, right? Okay. And this one has finite expectation which is equal to 1. And also we find that the product has finite expectation. Okay. So we have, they are all finite expectation. And so by linearity, which is proposition again, 72.8 dash 2. So this is equal to x hat square minus 2 expectation x hat y hat plus expectation of y square y hat square. Okay, we have that. Okay, so this is by proposition 7.2.8-2. Okay, -2, because coefficient can be positive and negative. Okay, and so this is equal to this is 1 and 1, right? So this is 2, and 1 minus expectation of x hay and y hay here. Right. So we have, now we plug into here. Okay. So we have that this is 2 times this. So we have that, that 1 minus expectation, because that this is greater than or equal to 0, so which means that 1 it will be greater than or equal to the expectation of x hay and y hay. Okay, 1 greater than that. Okay, and by the computation as before, okay, yep. Oh, I forgot to mention that this one is finite, but this is the square root of square. Okay, and the expectation of xy. Sorry. So we plug in to the definition here. All right, so this one, okay. This one is so this is finite, and so, but this is equal to this one, okay, and so this implies that not finished yet, okay. So this implies, okay, this implies that the expectation of xy is finite, exists. And it's finite. I'm sorry, I haven't finished yet this part, because this is just show that the product of x hay and y hay exists and finite, and then when we plug into the definition of x hay and y hay, we know the numerator will be exist and finite. Okay, because that these two, this second moments has been assumed to be finite here. Oh, and well, here we have finite second moments here. Okay, so they have finite second moment. All right. Okay. Now, right, and but by doing the same calculation, this is expectation of xy, and the denominator would be here. Right. And this inequality saying that if and only if we multiply both sides by the denominator, so we move that there, we see, okay, that expectation of xy would be less than or equal to the square root of expectation of square here. Okay, and so this is saying that the if we take the square, okay, we have, oh, by the way, there are some flaws. So I think I have to, all right, be careful. Now, so this is, oh, okay. Okay, sorry. I have to, sorry about that. I think that would be enough. Okay, so I will use here. This is equal to square root okay, and expectation of xy. Okay, so this ratio is finite, and I think I need the expectation of the absolute value. So this implies that expectation of, okay, finite. All right. So, all right. So, oh, okay. So this is finite, and then we have okay. So that this expectation is exists and is finite. Okay. So now I think the question here is that even though this is less than the square root of this one, but if the expectation is negative and has absolute value greater than the right-hand side, when you take the square, then the square of the left-hand side may be greater than the square of the right-hand side, which is not what we want, right? So we have to remedy this flaw. Okay, so I think it's better to okay. So it's better to use, okay, sorry. So I think we don't need to do it. So I just do it from here. Okay, so I use this inequality. Okay, so to use that inequality, right? We will take okay, right. Okay, I think, right. So the purpose for this is to show that the product x and y has finite expectation. Okay. Now for any a, b, okay, in R, this time we consider ax plus by. Okay, so that so this is greater than equal to 0 here. Okay, all right. So, and this implies that the expectation, I use minus sign. So the expectation of ax minus by square would be greater than equal to 0. So we have that. Okay, so we use this inequality. So again, this is by proposition 7.4.8 dash 1. Okay, we have that. And from that, equality holds. Okay, so equality holds if and only if. So the equality holds if and only if that ax minus by equal to 0 with probability 1. Okay. All right, by proposition 7.4.b. Okay. Now, okay, now we multiply out this product. So we have a square. So we have a square and e square. Right, maybe I use, but maybe which is equal to a square x square minus 2ab xy, all right, plus b square y square. Okay, and once again we can apply the linearity of expectation, because x square has finite expectation, the product of xy has finite expectation, right? And y square has finite expectation. Okay, so we have equal to square minus 2ab expectation of xy plus b square expectation of y square. All right, so this is by proposition 7.8 dash 1 dash 2. Okay, dash 2 here. And then we will try to make a perfect square. So we take out the expectation of x square here, okay, and so now we have a square minus 2ab, okay, and and here is expectation of xy divided by expectation of x square plus, okay, b square and expectation of y square, and here so now because by doing the perfect square we have this a b, so we need a b square and e xy e s square here. Okay, right now, so and so now we have b square e y square minus, because we add this term, so we have b square and expectation of xy square and expectation of x square. Yeah. Okay. Okay. Right. And so now the perfect square, we have x square and a minus b expectation of xy and expectation of x square plus b square divided by the square. So we have the square here. X square. All right, and this here we have e x square that okay, so we have if we multiply, so now we have square e y square minus e xy square. Is that correct? Oh, right. Okay, so we have to multiply with this. Yeah, so I'm sorry. This one here. Okay. All right, so that because when we subtract this one, we have to multiply with this vector. All right, so that the denominator here, it's just expectation of x squared. Okay, so yeah. All right, and so here, this is not square. Okay, so we have the same common vector b square. Okay, and if we move the denominator out of these differences now, so we have to multiply with this one to there, and we have this. Okay, that's good. All right, so you see that we begin with this, and the expectation, this is greater than or equal to 0. Okay, so we know this is greater than or equal to 0. And the equality holds. All right, if and only if ax minus by, okay, is 0 with probability 1. Okay, so we know here probability 1. Great. Now, and as we know, this is non-negative. This is actually, by our assumption, this is positive. And this one is non-negative, okay, because this is square. Okay, so that to make sure that this is true for all AB in R, okay, for AB in R. So that if this difference is not equal to 0, if this difference is not greater than or equal to 0, so if the difference is is negative, if this is negative, then you know we can make this term to be 0, right? So by given a proper A and B, okay, for example, we let A equal to B times this ratio, and so this is 0. And the B can be arbitrary, right? So this is positive, okay? And when this is negative, then the sum would be negative. So this is a contradiction. So that this is true for all AB in R, okay? In R. Okay. All right, and so this give us, so this is true, give us that the expectation of, so this must be non-negative. Okay, so now we have the expectation xy square should be less than equal to the expectation of x square and expectation of y square. Okay. Okay. So this must be true. All right. So this is the inequality here. This inequality here. Okay. And equality holds. Equality holds. Equality holds means that this become to 0. Okay. So as we know, we have equality, even only if that this is 0, as we know, and if this is 0, okay, for AB, we send AB there. So now we will okay. So if the equality holds, and the equality holds saying that this is 0 and this is 0. Okay. So the one way is that equality holds. Okay. So equality holds that if only if that expectation of xy square is equal to okay. And also A is equal to B expectation xy and the expectation square. So we have the relationship here. Okay, and so which means that okay, So it depends on. So we have A, B has this expression. So if so it depends on A and B. So that x is equal to A B y with probability 1, or y is equal to BAX with probability 1. Okay. Okay, so this shows that the equality holds. Okay. Okay, so we can see A and B should have this relationship, of course, and also so you can see that it depends on whether A is or B is non-zero. Okay. Okay. Right. So so for example, you can let B equal to 1, and the A would be this ratio. Okay. Okay. And so that from that this we will know when B is 1, so Y becomes to, so this is becomes to expectation of x squared is y of x, right, in this case. So if we take B equal to 1 and the A, or yeah, so you can, the ratio can take, when when B is non-zero, so you can have that one, or well, so this is the Schwarz inequality. Okay. Okay. For further discussion, we write down the following proposition. All right, so let x be a random variable. Okay, now if the expectation of the rth power, okay, of x is finite for some r greater than or equal to 1, then the expectation of x with the x's power also finite for all x in between 1 and r. Okay. In particular, if r equal to 2, right? So if E has the second moment, because that because this is if and only if exists and is finite. Okay, so the absolute value of the R power of x is finite, if and only if that expectation of R power of x exists and is finite. Okay, now, so, okay, and so the proof, right? So this is saying that expectation of x exists and is finite. Okay. All right. Now, by a proposition, okay, by proposition 5.2, I think 5.2.1, okay, the expectation of XR x of x, okay, where is the CDF of x, okay? So you CDF of x, because that this is the a function of non-variable x there. And we know this is finite, okay? This is from the given condition. Now, okay, now so this is now we look at this integral, the Riemann-Stieltjes integral here. All right, and we will, so we let for all x such that x is less than 1, okay? Okay, plus x for all x greater than equal to 1. So this is x R power. Okay, so now, so this is, as we know, this is, you can say this is x in R. Okay, so we split the integration over the whole real line into two parts. One is in over this open interval. This over the union of two infinite interval. Okay, so we have these two. And so the upper bound, because that within this region, the absolute value of x is greater than 1, so we can replace the integrand by 1. Okay. So we can replace them because the integrand, this integrand will always less than 1. And for all x such that greater than or equal to 1, then the r's power is greater than the s power. Okay, since greater than or equal to, okay, for all x greater than or equal to 1. All right, I have to say, since r is greater than or equal to x, greater than or equal to 1, so the r's power greater than or equal to the x power, okay, for all greater than or equal to 1. Okay. So if the magnitude of x is greater than or equal to 1, then larger power give you a larger number. Okay, so that this integrand is upper bounded by this integrand. Okay, and we know that, so this is less than or equal to, and this is the probability that less than 1, this event, and the integral over this region is less than or equal to over all the real line. Okay, but this is finite. This is always bounded by 1, and this is finite by assumption. Yeah, by assumption. So that this is finite, and we have done. Okay. Okay. So we have this result. So when for example. Okay, so by the previous proposition, if a random variable x has a finite second moment, i.e. expectation of x square, then it has a finite expectation, i.e. Ax exists and is finite. Okay. All right. So to have a finite second moment implies that to have a finite expectation. Okay. Of course, you can generalize the result. If a random variable has nth moment, then it will has n minus 1 moment, has 1 minus 2 moment, etc., up to the first moment. The first moment is just the expectation. Okay. Okay. All right, and so now we can define a concept called covariance. So the covariance between two random variables, x and y, all right, with finite expectations, finite second moments, sorry, finite second moments, All right. So now when we consider two random variables x and y with finite second moments, so x has a finite second moment, y has a finite second moment. Right. Then we can define the covariance. Okay. So the covariance and denoted as COV xy. Right, is defined as here. Defined to be x minus expectation of x. Okay? This difference times y minus expectation of y. All right. So because they have a finite second moment, so by the previous proposition, both x and y has a finite expectation. So Ex is a finite number, Ey is also a finite number. Okay, and then that so that their product. Okay, and so that it has the variance. Okay. So I have to make a remark. All right, since x has and y, okay, since this is finite, this is finite, right? X and y has finite expectations. Ex and Ey. All right, so that's the variance, okay, of x, which is the difference of second moments and the square of the expectation. Okay. Okay, so the variance by our definition before, this is expectation of x minus expectation of x square. Okay, this one, which is okay. All right, so this one is also finite. So the variance of x is just the second and central moment as we defined before, right? So this is the second central moment. Okay, so this is finite. Also, the variance of y, which is y minus expectation of y, take the square. Okay, so you can see the variance of y is the second central moment, and it's also finite. Okay, so we have that. Okay, so that this random variable, all right, has the second moment. This random value is the difference as the second moment. So by Schwarz inequality, their product, all right, this product has finite expectation. Okay, so that the covariance of between two random variable with finite second moment, this covariance must be, okay, a real number here. So this must be in R. So it's well defined. So that I have to say, oh, yep. Okay, so that. Okay, that's covariance of xy exists and is finite. Okay, so this number exists and is finite. Okay, so all right, so remarks 1 here. Second, when we multiply them, okay, by definition, as we know, okay, and so this is xy, okay, minus exy minus x expectation of y plus there. So this is a constant. Okay, and by linearity, because we know this product has finite expectation, okay, by Schwarz inequality, okay, since x and y, they have finite second moment, so that, all right, and y has finite expectation, x has finite expectation, and this is constant. So by linearity of expectation, so this is expectation of y, and this is expectation of x, expectation of y, plus the constant. Expectation of constant is just the constant. So by proposition 7.2.a-2. Okay. And so when we cancel, so now we have a formula. So covariance of xy is equal to the difference between the expectation of xy and the product of the expectation of x and the expectation of y here. Okay, so we have this formula, quite useful. A third, okay, if x and y are independent, okay, so if x and y are independent, we have that this identity, right? So we do identity by proposition 7.2.b. Okay, so we have this proposition. So that the covariance of xy to be 0. Okay, so if x and y are independent, then the covariance of x and y is 0. However, covariance of xy is 0 does not imply that x and y are independent. Okay. we can take a concept example. So this, for example, okay. For example, consider a random variable x with the following distribution. So with the following distribution, x equal to 0, will be x equal to 1, will be of x equal to -1 is equal to 1/3. So x is discrete with 3 possible values, 0, 1, -1, with equal probability. All right, and a random variable y defined by the following way, so if x omega is not equal to 0, then it's 0. But if x omega is 0, then y omega is equal to 1. Okay? So define here. Okay. So you can see that actually y actually is the indicator of the event that x equal to 0. Okay, so you can see. Okay, so y actually is the indicator function of this event. Right. Okay. So we see that then x times y, right? So x times y, which is equal to x times indicator of x equal to 0. Okay. Now, so which says that if x equal to 0, right, x has 0 value, then indicator is 1. So 0 times 1 is 0. But if x has value non-zero, then the indicator is 0. Okay. So anyway, this is called a 0. Okay. So the product always equal to 0. Okay. So that their expectation. So the expectation of this product is 0. Okay. And from here, we know that the expectation of x 1/3 times 0 plus 1/3 times 1 plus 1/3 times -1. So the expectation is also 0. Okay. So 0. All right. So that of course the probability of y, the expectation of y, because this is expectation of indicator, and so this is the probability of x equal to 0, and this is 1/3. Okay, so the expectation of y is 1/3. All right. So now we have expectation of xy, which is 0, as we just calculate, and this is 0 times expectation of y, and which is expectation of x times expectation of y. Okay, all right. And so this implies that the covariance of x and y is 0. Okay, because that. All right, so that the covariance is 0. However, x and y are not independent. Why? Since if we compute the event, so the joint event probability of probability that y equal to so probably y equal to 0. Maybe I will say, okay. So y equals 0 and x equal to 0, right? We look at the joint probability. So what is that? Y equal to 0. Okay, y equal to 0 is the same as that probability that x not equal to 0 and x equal to 0. Okay. And so this is the probability of the empty set. So this is 0. So the joint probability is 0. Okay. All right. So from the definition, you know that. And but so it's 0, and of course it is not equal to say 2/3 times 1/3. Okay, and the 2/3, which is y equal to 0, probability of x equal to 0. Okay, probability equal to x equal to 0 is 1/3. Okay? And this probability is probability that x not equal to 0. Okay, when x equal to 0, y equal to 0 means x not equal to 0. Okay, and this is what is that? So this is the 2/3. Yeah. Okay, and this is 1/3. Okay. So the joint probability of these two events is not equal to the product of the respective probability. Okay, so that's why x, y are not independent. Okay, okay. So this is a counterexample, as you can see. All right. Now we have a further proposition to have. 7.4.e. Okay. If x and y are two random variables with finite second moment, then ax plus by, so their linear combination, all right, has a finite second moment too. Okay, for all a, b in R. and put as an exercise. Okay. All right. So hint. All right. Apply Schwarz inequality. Okay. Apply Schwarz inequality. Okay. So so if x and y have finite second moments, then any linear combination of x and y has finite second moment too. Okay, so that there are two propositions in section 7.4 of the textbook, and so I would like to state them. And one of them is actually given, follow from our previous theorem. So so proposition 7.4.1 in textbook. So if x and y are independent random variables, then for real measurable real value functions g and h on R, the expectation of g of x times h of y is equal to the product of the expectation of g of x and the expectation of h of y. Okay. All right, and so this is a special case of proposition, a special case of proposition 7.C. Okay, so we have proved before. In this proposition, we're considering two collections of random variables. Okay, so they have that. Okay, another proposition given in the textbook, proposition 7.4.2 consists of actually 4 statements. Okay. First of all, covariance of xy is equal to covariance of yx. So covariance is symmetric between these two random variables. And this is due to the fact that they are the difference. So you can exchange the order of x and y, right? You can exchange the order of this product, give you the other one. Okay. The second statement is that the covariance of x and with itself is actually the variance of x. Okay. And the reason is the same because from here, because xx, So x squared and EX squared. Okay, because y equals x. All right. So and the covariance of x with itself is this formula, but this is actually the variance of x already. Okay, so that they are actually very simple results here. Okay. The rest two statements are given here. The covariance of AX by, which means that if we multiply scalars for each random variables, then this is, so now we can check out both scalars, all right, here, out of the covariance. Okay. And in particular, the variance of AX, okay, as we know, this is the A square variance of X, okay. Right. So variance of AX, okay, is just here. So variance of AX is the covariance of AX and AX, okay. And so AX, we can take both A out of the covariance, so you get A squared. Okay. And the proof also quite easy, as you can see that. So this is actually, by definition, this is the expectation of AX by minus expectation of AX, expectation of by. All right, and by linearity, this is actually AB, by linearity of expectation, and B, okay. And so you can have AB out. Okay, and this is actually this formula here. Okay, and the fourth one is that the covariance of the sum I from 1 to n. So it's the sum of nx sub i's and the sum of m y sub j's. Okay, there. And this is come to double sum of the covariance of xi and yj. Okay, xi and yj. Okay, and actually, this is from by applying the linearity of expectation. So that okay, so this is equal to. So as we can see, but this is expectation of summation minus okay, right, so this one. And first of all, this is the product sum, become to sum of product. So this is expectation of I from 1 to n, summation j from 1 to m, and this is xi, yj. Okay, so now we have double sum. And we apply linearity of expectation. Okay, and then here we have now here, okay, Okay, and so that bilinearity of the expectation again, this expectation of x, y, j. Okay, and this is product sum become to sum of product. Here. So now they both have double sum here. So that we collect them together. Okay, and finally we have so this is equal to, here is the covariance of xi and yj. Okay, we have that. And of course that to have these formulas, we assume, so we will, here, we will let, so here we will let x, y, and x1, x2 up to xn, y1, y2 up to ym be random variables with finite second moments. Okay? So to apply this proposition, all the random variable involved should have finite second moments. So that is the requirement to apply this proposition. Okay, and so now from proposition 7.4.2-4, the fourth property. So we have the variance of the summation from 1 to n xi. Okay, so variance of the sum of n random variables. Okay, and this is actually covariance of this sum with itself, right? With itself. All right. So now we have, so by this one, j from 1 to n, and the covariance of xi and the xj here. Now, and we have n terms that I equal to j. So the covariance of xi here, plus 2 times the summation that I would be less than j would be less than n, and the covariance of xi and the xj. Okay. All right. So this is corresponding to I not equal to j, and we purposely use j greater than I. Okay. Because that, and why we have 2? Because of the symmetry here. In 1. Okay. In 1. xi, y, xi, xj, covariance xj, xi. Okay. So now, so we have put 2 here. Put 2 here. Okay. So in particular, okay, if x1, x2 up to xn are independent, then the covariance of xi and xj will be 0 for all I not equal to j. Because when these n random variables are independent, then any 2 of them, all right, should be independent. Okay. Okay. Because you can remember this one midterm 2 problems. I ask you to do so, right? So actually, if we have n random variable to be independent, then any subset of this n random variable will consist of independent random variables. So we have covariance is equal to 0. So that this term is 0. Okay, and then the variance of the sum is equal to the summation of the variance of hxi. Okay, so this is true when they are independent. Okay, so this is a very good formula to use. Okay. All right. Now, an application of Schwarz inequality is in the following proposition. F here. For any 2 random variables x and y with finite second moment. Okay. Then we have an inequality. So the covariance of x and y, okay, and take the square, is upper bounded by the variance of x and times the variance of y. Okay, and equality holds if and only if either y equal to alpha x plus delta or x is equal to beta y plus gamma with probability 1. Okay, for some constants alpha, beta, gamma, delta. Okay. All right, and the proof is now because x and y have finite second moments, so they have finite expectations, and so we can define so that z to be x minus its expectation, and the w defined to be y minus its expectation. Okay. Okay, and so by Schwarz inequality, okay, i.e. proposition 7.4 point, let me see, the Schwarz inequality. We'll give case C here. We have okay, that the expectation of ZW, so ZW square is less than or equal to expectation of Z square times expectation of W square. Now, all right, we plug into the definition. So this is expectation of X minus expectation X multiplies Y minus expectation of Y. Okay, but this expectation is just the covariance of XY. Okay, so covariance of XY is actually expectation of Z times W. And what is this? The expectation of Z square, X minus. Okay, so this has become to the second central moment, right? So this is the variance of X. And here, this is the second central moment of Y. So that is the variance of X times the variance of Y. Okay, right? So you can this inequality is indeed the Schwarz inequality if we define Z and the W in this way. Okay, and from Schwarz inequality we know that equality holds. If and only if equality holds, if only if W here W is equal to alpha Z, okay, or okay, and so let's see, W equal W actually is equal to Y minus EY, right? And this is alpha X minus EX. Okay, here. With probability 1, okay, and also our Z equal to beta W, okay, and this is X minus EX equal to beta Y minus EY with probability 1. So that so Y is equal to alpha X plus EY minus alpha EX with probability 1, or X is equal to beta Y plus expectation of X minus beta expectation Y with probability 1. Okay, and we will later let this defined to be delta, and this is defined to be gamma here. Okay. Okay, so this is end of the proof. Okay, so So now, by applying the Schwarz inequality, we know the square of the covariance of x and y is less than or equal to the product of the variance of x and variance of y here. Okay. All right, so now we define the correlation. The correlation coefficient of two random variables, x and y, which are non-constant with probability 1, okay, denoted as rho, so the coefficient is defined as that the correlation coefficient rho is defined to be the ratio of the variance of x and the variance of y, okay? And this is covariance of xy. X and y are which are non-constant with B1 means that the variance of x is greater than 0. The variance y is also greater than 0. Okay. So we should exclude that kind of trivial case. Okay. Right. So that which are non-constant with B1, right? If and only if variance of x greater than 0 and variance of y greater than 0. And this is good by proposition 7.4 point B. Okay, we have proved before. Because the variance is the second moment of x minus its expectation. Okay, so if the variance is 0, which means that x is equal to its expectation with probability 1, and its expectation is a constant. Okay. Similarly, variance y is 0 if and only if y is equal to its expectation with probability 1. Okay, so that they become two constant with probability 1. Okay, but they are non-constant, right? So that means that these two variances should be positive. So that's why we can put into the denominator. Okay, so this will become to be well defined. Okay, and from the previous proposition. Now, so from the previous proposition, from proposition 7.4.f, okay, that the square is this. So which implies that covariance of xy, take the square, is less than or equal to the square root okay, yeah. And so if we divide both sides, so this and equal to 1. Okay, so if so this inequality implies that and this is the correlation coefficient. Okay, so we know in this case the correlation coefficient is in between -1 and 1. Okay, so we have this inequality here. Okay, so this is from there. Okay. And so we have the following result. So proposition 7.4.G. So for two random variables, x and y, which are non-constant with probability 1 and have finite second moments. Okay, we have one. The correlation coefficient is equal to 1 if and only if y is equal to alpha x plus delta. Okay. With probability 1 for some constant alpha greater than 0, but delta can be arbitrary. So they are called positive correlated. So the y is just a positive coefficient alpha times x plus arbitrary constant. Okay, so this is if and only condition. And second, the correlation coefficient is equal to -1 if and only if y is equal to alpha x plus delta with probability 1 for some constant alpha less than 0 and the delta arbitrary. Okay. So there are two cases because the correlation coefficients reach the extreme values, either 1 or -1. They are very special, right? And so in this case, if and only if that y is a positive constant times x plus an arbitrary constant delta here. And when they are -1, the correlation coefficient is -1 if the scale coefficient alpha is negative. It's negative. Okay, and this is the proof. Right now, since okay, so we can apply because x, y has finite second moments and they are non-constant. So we can apply the proposition 74.f here. Okay. So by proposition 7.4.f, okay, the coefficient is -1 plus 1 if and only if, right? So plus or minus 1 if and only if that the covariance of the square is equal to the variance the variance of x times the variance of y. Okay, so as we can see, okay, from here. So so this is bidirection, okay, and bidirection here. So this inequality implies that the correlation coefficients has absolute value less than or equal to 1. And equality holds. Equality holds means that the correlation coefficients, this is equal to, as we know, this is just equal to rho xy, right? So equality hold means that rho xy is equal to +1 and -1, okay? So it's this way. And so if and only if, okay, y equal to alpha x plus delta with probability 1, okay, for some constant. Okay, so for some constant alpha not equal to 0, and for some constant r and delta in r. The reason why alpha cannot be 0 is because if alpha is 0, then y is a constant with probability 1, which violates our given condition. Okay, so alpha must be non-zero. And you may say, how about the case here? Because we have two cases, either this or this case, right? Okay, but if in this case, beta also cannot be 0. Okay, so beta must be non-zero. So if beta is non-zero, then we can do, if beta non-zero, then this is become 2 1 over beta here, and minus beta gamma here. Oh. Okay. X here. So again, y can be expressed as a constant, which is non-zero constant times x, and add some real number here. Okay. So in either case, we have the same. We have this formula. Okay. Okay. Right. Because beta cannot be 0. Otherwise, x become to a constant with probability 1. Okay. Okay. So this one only way to go is means that y must be equal to alpha x plus delta. Okay, so this is if and only condition there. Okay, and so right. So this is plus minus 1. We have this one. Now, right now, we really do the calculation. So we really do that. And so this is equal to, okay, so in this case, maybe in this case, so we compute so in this case, we compute the correlation coefficient. So that would be x alpha x plus delta here. Okay? All right? And so this becomes to be, by definition, variance of x and the variance of alpha x plus the delta constant, right? And here we have covariance of x and alpha x plus delta. All right? But the constant here will have no effect. So covariance of x and alpha x here, and the variance of x and the variance of alpha x. Right? So the constant has no effect in the calculation of the variance. Right? And we apply the formula. So this is alpha, covariance of x here. Okay. And here we have variance of x and times alpha square and the variance of x here. Okay. So finally, we have alpha divided by absolute value of alpha, and the covariance become to variance of x, and this is the variance of x, so that this is alpha. Here. All right, and so you can see it is either 1 or minus 1 if alpha is positive, if alpha is negative. Okay, and we have done. Okay, so in this case, the correlation coefficient after the computation is either 1 or minus 1, depends on alpha is positive or negative. Okay. Okay, and so now we have this expression there. Okay, so a final remark to make here before we end this class lecture is that the correlation coefficient rho xy, all right, is a measure of the degree of linearity between two non-constant okay, of course, with per B1 random variables x and y. Okay. Right. So, and so a value of rho xy near +1 over -1 indicate, right? So indicates a high degree of linearity between these two random variables. Where A is a value near 0 indicates that such linearity is absent. Okay, so as you can see, the extreme case from this proposition, if the correlation coefficient is exactly 1 or minus 1, then x, y are related linearly, perfectly. You can see almost perfect with probability 1. So y is a linear function of x. Okay, and so you can imagine if the correlation coefficient is very near to 1 or very near to minus 1, then they are have very high degree of linearity between them. Okay, so this case is that if you plot, you will observe many outcomes, then you will have. So if you plot, you point x of omega 1, y omega 1, a point here, so that you may have some linearity here. Okay, so this is x omega 2, y omega 2, and this is x omega 3, y omega 3 points, and you have this point about x omega 4, y omega 4. Okay, so you plot the point, you find that if you have many outcomes, and you can see that they are very near to a line here. Okay, you are very near to a line here. Okay, so which means that x and y are highly has high degree of linearity between them. But within 0, which means that the point will be scattering arbitrarily. Okay, it's very hard to that there is any linearity between them. Okay, so this is about x omega I, y omega I. Okay, so the point when you observe, say n outcomes, and you plot corresponding points of x and y, you find that they are scattering on the plane. Okay, and so that's actually their correlation coefficient is very near to 0. Okay, this is one observation. The other observation is that a positive value of rho xy. So if you compute rho xy, which is positive, indicates that y tends to increase when x does. Okay, so when x increase, then y increase. Okay, whereas a negative value of rho xy indicate that y tends to decrease when x increases. Okay, so very interesting, right? So it's in statistics or in a particular situation, we many situations we want to know the relationship between two random variables. Okay, so we usually compute their correlation coefficients. Okay, and to see whether the value, and from this remark we know that if we get value near to +1 -1, then x and y are actually with high degree of linearity between these two random variables. Okay. Okay, and if they tend to 0, then they will decrease. And okay, and so we give a name for the case that and also x and y are called uncorrelated if their correlation coefficient is 0. Okay, this is 0, so it's uncorrelated. Of course, if x and y are independent, then their correlation coefficient is 0, because their covariance is 0. Okay. But the reverse, the converse is not true. When x and y are uncorrelated, means that the correlation coefficient is 0. This does not imply that x and y are independent now. Okay, so that independence is stronger than uncorrelatedness. Okay, so uncorrelatedness is a weaker condition. Okay, to have. Okay, so I stop here, and so this is the end of section 7.4. Okay, so next week I will start with section 7.5. Okay, so that's it.